In this video, we're going to be looking at digital representation of sound in a computer system. So first of all, we need to look into analog sound, which is sound in the real world. And as you can see, this waveform, this represents an analog sound wave. And as you can see, over time, the amplitude of the wave is changing. So the height of the wave is changing continuously over time, which is what gives this wave its characteristics. Computers can't store analog sounds, okay? Computers can only store things in digital format, which means that this signal needs to be converted to digital, which means a series of binary numbers which represent the positions of these waves over time. So what does that involve? What does analog to digital conversion mean? Well, first of all, analog sound is received by a microphone in the real world. Okay, that signal is then converted into an electrical signal. This is then put into an analog to digital converter within a computer system, and what that does is it measures the amplitude or the height of the wave over time. Those measurements are called samples, and they're taken at regular intervals. So over a course of a second, at every regular interval, okay, that sample is taken, so the height of the wave is taken. It's important that those samples are taken at regular intervals, as in each sample is taken with the same period of time in between each. The values that it takes, so the amplitude of the wave, the height of the wave is measured, and then it's rounded to the nearest level, and that's called quantization. And then the values are then stored as a series of binary numbers which can be understood and stored on a computer. So what is a sample? Okay, so as you can see from this picture here, we have our continuous analog wave, okay, continually changing over time, and what's changing is the amplitude of the wave, so the height of the wave. At regular intervals, okay, so you can see that each of these samples are taken with the same period of time in between, the height of the wave is recorded, okay. So the accuracy of these samples and where they're taken, so as in how close they are to the wave and how good a representation they make of the wave, is dependent on two things. The sampling frequency, so how often a sample is taken every second, and the sample size, okay, which represents the number of bits that are used to store each sample. So we're going to look in a bit more detail at sampling frequency first. So this is the number of times a sample is taken every second. It's measured in a value called hertz, and 1 hertz means that we're taking one sample every second. So if we were to record a wave and sample it at 1 hertz, that means that one of these samples will be taken every second. The higher the sampling frequency, obviously, the more samples we take every second, the better the accuracy of the digital representation. So you can see here, if we were to join up these dots on this wave, we'd get quite a poor representation of this wave because we'd miss all of the curves in between each sample. Whereas clearly, if we were to take samples at more regular intervals and record more samples within there, we would get a better representation of the wave, a more accurate representation of the wave, when we were then to go on to redraw it if we were extracting sound from a computer and playing it back again. So the higher the sampling frequency, the more accurate the digital representation of the sound. The sample size is the number of bits used to store every sample, okay? So you could record sound by using 8 bits for every sample, so each one of these blue dots will be represented by an 8-bit binary number if that was the case. CD quality sound is recorded at 16 bits, which means that every one of these blue dots would be represented by a 16-bit number. The higher the sample size, the more accurate the representation of the wave. The reason for that is the higher the bit rate, the more of these quantization levels that we have to record to. So as I said at the start, every time that a sample is taken, the amplitude of the wave is measured, and then it's rounded to the nearest quantization level. So you can see here with this third sample, it's quite close to the quantization level, and therefore we get a relatively accurate sample there. But as you can see, at this point here, when we take this sample, the nearest quantization level is quite far away from where the wave actually is. So this means that we're getting quite a poor representation of the sound. So the higher the sample size, the more quantization levels we have along here, which means the better the accuracy, because we don't have as far to go to get to the nearest level whenever a sample is taken. So what does this mean for the size of the sound file? We've already covered that the better the sampling frequency, the higher the sampling frequency, the more accurate and better quality sound that we get. Also, the bigger the sample size, the more accuracy we get as well. But there is a trade-off from this. Obviously, with more samples being taken and with higher sample sizes, so more bits representing each sample, that means that it will result in a higher file size. So if you want very, very high quality and more accurate sounds in a digital representation, you will have to have files that do have a higher file size.